right, thank you very much, everyone. So I'm Josh, and the other panelists were already introduced. I'm going to start off with just very brief introductory remarks, and then we're each going to give short opening statements. I'm not sure how much debate is going to be, because I think actually there's a really interesting, remarkable agreement among many of the panelists in the broad sense about the kind of path we're on. But what I'd like you guys to say in your introductory statement, I'd like you to focus on is what path, so first of all, let's say of the five of us here, I'm sure you know something about each of us, but I'd say 4 out of the 5 of us are actually working on AI as one of our main things. Nick has been more of a thinker about a broad range of paths and their implications. And so I want to start off by asking the four people here, and I'll go at the end and say a little bit about my view. What path to AGI are you on? Yoshua actually just gave a really great talk explaining that, so you could summarize it or just say that that's right. What it was. But what path are you on? Which means, like, what's your goal and what's your roadmap? Why did you choose that path? And how far along on it do you think you are or your part of the community is? And then we'll dig into that a little bit and think about next steps and stuff. So, Irina, do you want to start?
Sure. Is my mic off? Okay. Yeah. So I think we all agree that there are multiple viable paths to AGI, and all of them come with certain trade-offs in terms of how long it will take us to get to AGI if we take that particular path, and what the resulting AGI might look like in terms of things like memory or computational requirements. So when I was making a choice of which path to pursue, the question I asked myself is, what is it that I want AGI to actually look like? And for me, I want AGI to do as well as humans on the natural tasks in our natural world. And so for me, it felt natural to look for inspiration at biological intelligence. And of course, in our world, we know that there exist numerous examples of biological intelligence. Each one evolved to kind of perform optimally in the kind of tiny slice of the universe that their body allows them to explore. And we know that these intelligences are very diverse, ranging from the distributed brain of the octopus to the centralized brain of the vertebrates. But also they share quite a lot of similarities. So, for example, if we look at the human brain, then we know that its cerebellum is shared with the ancient ancestors like the fish, and parts of the limbic system are shared with the lizards. Also, if you even look at the different areas of the cortex in a single brain, it's widely agreed that they share a lot of kind of computational principles and a lot of architecture, even though they might be doing very different roles, like visual cortex versus the auditory cortex. So it seems like there are some core computational principles that are shared between many examples of the existing biological intelligence that we still don't really understand. So for me, this is the path to try to figure out what are these principles. And I'm not talking about trying to replicate the minute details of like spiking dynamics, kind of the implementation details of how biological intelligence works, but what I care about are the kind of core computational principles. So if you know of Mars, levels of description is more of the algorithmic side of things. And another thing that I think is really important is that intelligence does not exist in the vacuum, right? If we had a completely random world, then we would not have intelligence. So there is something about the structure of our universe and of our world that enables intelligence to exist. So for me, it's really important to examine these embodied interaction between the brain and the world to understand where intelligence comes from. So this is my approach, trying to look both at the structure of the world and the kind of core computational principles of the brain to figure out what are these the principles that we can then port to the artificial substrate. And also I think this path is quite cool because even if we don't reach AGI, hopefully on the way we can discover quite a lot of interesting things about ourselves.
Okay, great. Go ahead.
Hi, my name is Yi, and from Chinese Academy of Science. I'm working on a brain-inspired approach for artificial general intelligence. So I guess our background is quite similar, but I do see the difference actually. Well, just now we mentioned that what do we really need for the realization of artificial intelligence? Do we need spiking patterns, activities like that? So to my extent, to my mind, I would say that science is in the detail. So my approach is more on the brain-inspired spiking neural network for realized artificial general intelligence. So when we talk to people, well, people say that, okay, you're working on brain-inspired AI, that means you're a connectionist. And then I would answer this question like this. So as a connectionist, do you reject symbolic AI? And people always say, yes, we don't really need symbolic AI. But my understanding is that for brain-inspired AI, what we need is not only the connectors, it's not only about a computational model and their self-organization of the network, but also how can the neural dynamics give rise to symbolic reasoning? So this is truly important. So in this case, I wouldn't say brain-inspired AI is connectionist. So I'm not the first one to say that. Like in 1955, when people have Western Joint Conference on Computer Science, there's a session a year before the AI first conference in Dartmouth. Say the Walter Pitts says that emulating the nervous system and actually emulating the hierarchy of final courses traditionally called the mind will actually come to the same thing. There is no doubt. So in this case, what I expect is that for brain-inspired AI, we need the synergy and collective efforts for both connectionist and symbolic AI, but more in the details, I would say. So all my work is based on single neuron modeling of different type of neuron and how it gives rise to different kind of functions and how these cognitive functions self-organize together to realize more complex multitasking and even AGI. And for more specific level of details, we're working on self-recognition, different levels of self-consciousness and fear of mind, so that I think this is of fundamental use for safe AI. I cannot expect a world that an AGI system without a sense of self that can really understand the world and interact with us. So I think the building block should be starting with very initial stage of self-consciousness, all the way down to fear of mind, cognitive empathy, and also emotional empathy. And then we could have the real safe AI.
Okay, great. I'll just say for myself, again, I think, you saw Yoshua's statement. We're all inspired by cognitive science and neuroscience. For me, I come out of cognitive science, and my fundamental goal is to reverse engineer intelligence in the human mind, and that means also the brain. But I'm approaching more from the functional, behavioral, and I'd say sort of software level of algorithms, as opposed to starting more from the network structures. And to me right now, what seems so exciting, the path that I think I'm on, is what is in some ways AI's oldest dream about how to get to human intelligence, going back to Turing's paper in which he proposed the Turing test, right? The dream of being able to build a machine that grows into intelligence the way a human being does, that starts like a baby and learns like a child. Turing proposed that famously as the only idea he had about how you could do it, and it's been promoted by, at these early AI conferences by Marvin Minsky, John McCarthy, in some sense all of the great AI thought leaders from the beginning. And Yoshua and I agree, very much, like we show the same videos. The idea of like what is that basic common sense that even those young kids have when they're playing with blocks or cups, right? I think there's a good reason for this as a scaling route to AI, because it's actually the only known scaling route in the known universe that we know actually works, right? A human child is the only learning system that reliably, reproducibly, demonstrably grows into adult human level intelligence starting from much less. So if we could reverse engineer how that works, then that would be a route. And it's also a route that we can measure. There are milestones and metrics, and there's an entire field of cognitive development that has, for the last couple of decades, made great strides towards actually laying out what that roadmap might look like. I'm always asking myself also, okay, well, if that's what we're working on and all these great people have thought about it, why hasn't it worked before, and why might it work now? Well, I think we're at a very important time, which is that the fields of engineering and the fields of cognitive development have both matured to the point where they can talk to each other. Where engineering, and just as Yoshua said, where engineering now can offer useful tools to the people who are trying to reverse engineer how babies' minds work, right? And where the field of developmental psychology has got enough qualitative and even quantitative insight that it can actually start to guide those fields. And hopefully they'll be mature enough to talk to each other. Okay? And in the work I've been doing as a cognitive scientist for the last 10 years or so, that's exactly what we've been doing. We've been building computational models of infants' perception, infant common sense, and the learning mechanisms which take that forward. So I'm excited, especially right now, about what I see as like the sort of key moonshot stage for us is roughly the stage of 18-month-old common sense. The common sense that is the height of where we get to before language comes into the picture, but which language builds on. Because I think that's where we have enough understanding on the science side and enough maturity in our engineering toolkit that we can really get there in a practical way. We're just at the beginning of that, because then you'd have to ask, well, what happens when language comes into the picture? And culture, I completely agree with Yoshua of the centrality of culture and the cognitive mechanisms of language and empathy and other kinds of things that support that as getting us, that's the real singularity for human intelligence.
That's right.
But I think we understand enough about that first step that it's extremely exciting to be working on that as a computational cognitive scientist and as an AI engineer. Okay, so that's the range of views, which in some sense we're all biologically inspired in some ways. Of course, there are other possible paths to AGI, and again, Nick has had a lot to say about the different, let's say, factors there. Do you want to comment on how you see the panelists here thinking, or other possible paths?
I mean, I agree. This looks like kind of the modal, most promising path, something roughly in this ballpark. I mean, maybe if one just to map out things, if one sort of indexes, say, on Bengio's intuitions and vision, and then one sees how could one diverge from that in different directions and get different sort of visions of this. So I think one direction would be to say we need even more inspiration from biology. Like we really need to capture the nitty-gritty biology, the exact dynamics of spiking trains and dendritic compartments and so forth. That could be a vision somebody would hold. So we really focus more on neuroscience than on AI. And at the extreme of that, you have people who think we will first get to machine intelligence by not just being inspired by the brain, but by replicating the whole thing with some kind of whole brain emulation, right?
That's not going to work.
Which I agree looks much less likely. But if one kind of maps out the space of possibilities that are championed by at least some, non-stupid people, then that would exist on that map. Then one could go in another direction and say, well, we can abstract more from the brain part and look more at the mind part, maybe. Good old-fashioned AI looks dead, but there are other ways in which you could go up a level of abstraction. You could think maybe some kind of evolutionary algorithm, like some algo search, would, with enough compute, be the way we get there. So, like, do away with all of this human scientists trying to figure out the mechanisms and just hope we find it in a big enough search space. Or maybe something that you find the right kind of idealization, and it's something different, something more principled, something more based in nature, some kind of graph, something put together by repeated application of some simple functions that you build up, and then this looks like a kludge. The neural net approach might look like a kind of kludge way of approximating what there is a cleaner mathematical path to. Could be the case. I guess you could take a more circuitous route and say that, well, hey, what we need to do is we are right now kind of incapable and need to first enhance humans, either collectively to improve our collective intelligence as a scientific community or individually with biological enhancements, and that's what will be what creates machine intelligence. And so I think this kind of maps out a little space, and one can maybe put different people's approaches in there. And I have an impression that you think something between Bengio, but with a little bit more maybe theoretical understanding of the modules and specific things that human infants do, and then maybe kind of
You're
more,
talking to me,
more
yeah.
cognitive science. Like
Yeah, I
kind
mean,
of,
I guess I would say, well, or are you feel free to finish, or I can.
yeah, no, but and you might
can
think
try to
you need
create some
more
debate.
capture biological
Yeah.
detail, and
Yes.
I guess you are kind of similar in the level of abstraction of inspiration that we need to.
Yeah, so if we could talk about our different levels of abstraction, yeah, go.
I think talking about different levels of abstraction is
Yes.
an interesting place to discuss.
Yeah,
I might want to comment on Nick's point on evolutionary
Yeah,
computation.
go for it.
So actually, my view for intelligence is not only about learning. For short term, it's like milliseconds to days, but also for decades of development and for billions of years of evolution.
Yes.
So this is why in Mac's book about Life 3.0, saying that for AI, we got an opportunity to rewire both software and hardware. So let's say in the biological brain, what we have for one concrete example is that we have excitatory inhibitor neuron. So why not 50 and 50, half and half? It's actually not in the brain. We're actually in the sensory cortex. Approximately 15% of them is in our mammalian brain. And when I'm developing a spiking neural network for amnesty recognition, is actually, I found that the 15% of the inhibitor neuron is the optimal for amnesty recognition. So that means through decades of evolution, what the biology found is a optimization procedure that help us to find the optimum to solve problems. So in this case, now we got the power of learning and development and also evolution, so that you can rewire the whole system design, not only for parameter tuning for those connections of the building blocks, but also to change the building blocks and how they connect to each other. So this, I guess this
very
is the
important
way.
that the scientific approach looks and says, okay, there's adaptive processes. You could call them learning in some sense across all these time scales, from the millisecond scale to millions of years of biological evolution, and with cultural evolution also in the middle of that, right? And I think there might be important differences of opinion there, right? Like you could say there's another path, right, which you maybe referred to a little bit, that is very well represented, I think, in some parts of DeepMind and OpenAI, for example, and it's often put out there as what people are maybe scared about or excited about, is a kind of evolution, the sort of massively distributed deep RL as a synthetic model of evolution. So where we're going to unleash this evolutionary process with enough games, whether it's Dota or Capture the Flag or the entire OpenAI gym universe. And I think that's an interesting thesis, that toolkit might be able to, in some sense, get a kind of evolution. But then there's a question of, can it do enough of the structural construction and reconstruction that biological evolution has done that you're pointing to, and there's more questions, I think.
So I want to add a few things. First of all, regarding the different paths that you mentioned, I think some are safer than others. I think this conference is a lot about safety, and in particular, I believe that if we more or less stick to the human-like intelligence, we end up with something much safer than other options, because we kind of know the limitations of human minds. And they're not infinite, even if we, as I said, if we had bigger minds. So one thing that's connected to this, which I think is also a good engineering reason for going that way, it's connected to what Irina was talking about when she talked about the sort of shared principles between intelligence in different animals. And presumably those principles, if we were to understand them, would allow us to build intelligent machines. Now there's, those, you can think of those principles as like a small set of laws, like the laws of physics, and that would be amazing, right? I think it's like an amazing hypothesis. If this was true, that we could understand intelligence with such a small set of principles, then it would have amazing consequences. It would be, of course, aesthetically pleasing, but also it would make it much easier to build smarter machines, which could be a good thing or a bad thing, but it would be mostly building a kind of intelligence very close to human intelligence. And the other thing I want to mention is about the levels of abstraction. So the reason I chose to do neural nets in the early 80s, mid 80s, was because I felt that they were at the right level of abstraction between sort of low-level notions of how particular neurons are actually computing and high-level cognition, in the sense that with the neural net toolbox, and especially the one we have today, we can represent high-level cognitive computation, and we can also represent low-level things. Like one of the things I've been working on is how could brain do backprop, so low-level computation that gives rise to credit assignment. All of these things can be talked about in that language. So that's very convenient. One thing I want to mention also about those principles, there's a lot of effort in neuroscience and maybe to some extent in cognitive science to describe human intelligence through all of the things that we can do, and in the case of neuroscience, like which neurons are doing what. Sort of mapping out sort of huge encyclopedia of every function that the brain computes, where it's done, and how things are connected to each other. I think this is hopeless, right? It would take forever to understand the brain that way. If instead we can figure out a small set of principles that can give rise to this computation, then of course it would be much simpler, much faster to understand the brain. And the principle number one is learning, right? That you don't need to actually describe the function computed by the brain. You only need to describe, which is like a huge number of bits, right? You only need to describe the learning procedure, which could be very, very small number of bits, which could fit into your genome.
Yeah, I think a few comments on that. So in terms of language learning, I think I agree with a lot of what you said in your talk and now, but I think I see the prelinguistic stage of kind of learning basic concepts as really important.
Of course.
And
most animals are there, right?
Yeah, exactly. And I believe that the reason why children have this amazing vocabulary spread is because they've already pre-built the concepts, and now the task that's left is just like fast attachment of word labels to these existing concepts. And I think if we take AI like the non-human route, we have a danger of the AI learning different kinds of concepts than what humans have. And then it might actually be harder for it to learn our symbolic kind of labels for these concepts, which also means that then humans might struggle to actually communicate with AI. So then we might actually struggle to, there are safety constraints, right? So there are interpretability constraints that come from that. So I think that's kind of a point.
I think that's a great point, yeah. I mean, I think that if we want AI in general, whatever really form is going on inside, but if we want AI to live in a human world, to live safely, effectively, valuably, right, to be able to be an entity that humans can talk to, teach, and trust the way we do with other people, even people we haven't met before, then in some sense, right, at least there's got to be something like a Humanlike API, and at least in some sense, just as we have certain APIs to each other, right, that are justified by some common mechanisms at some level. I think it's a route not only both to safety, but also to some of the other dimensions of benefit. Maybe just to try to create some controversy. I don't know how much time we have. How much time should we take?
So if you have another 20 minutes.
Oh, okay, we have 20. Okay, good.
Including audience questions.
Oh, okay, great. Well, okay, so yeah.
So I can throw some controversy.
Well, let me just first respond to what Nick said and what you said, if that's okay, and then I'll try to create some, and then you can create controversy around that too, or like that controversy. So just to say, yeah, I mean, I think there is one difference is, I guess, coming as a cognitive scientist maybe as opposed to a neuroscientist. There are a few sort of stylistic differences, and it also relates to our orientation towards, say, classical AI, right? I mean, I think Yoshua thinks of classical AI as, well, they had certain goals, but not the right mechanisms.
That's
Whereas,
right.
I guess, my feeling, and I think that the sort of collective insight of the field of cognitive science is that actually symbols are important. There are really symbols in the brain. There are really symbolic languages of abstractions, symbolic systems in the brain. Okay? And it's remarkable how that works, and we don't quite know how it works. But that there's actually a lot of success we can have with the combination of several ideas, rather than saying, okay, so to me, I wouldn't say neural networks are the universal representation layer. I would say programs are the universal representation. Those programs could be differentiable programs of the sort that a deep neural network is, but they could also be, Lisp expressions. They could be grammars. And I think, to me, what's remarkable about the maturing engineering toolkit is our understanding of all the different possibilities of programs as models and as different ways to learn programs, right? If your models in general are some kind of program, then learning has to be something like programming. And one way to program is to write code by hand. Another is to as we've now just, found, have a big differentiable architecture with lots and lots of parameters, set up the right data set, and if it's end-to-end differentiable, then you can effectively tune and shape the program using stochastic gradient descent and such methods. But there are many others. And
But there's no programmer that programs
exactly, but
our
one of
cognition.
one of the most exciting things in machine learning, right, which has been somewhat independent of deep learning, but is now also drawing on things from deep learning, is what's sometimes called machine learning meets programming languages, or programs that write programs. So these are people coming in with a different technical toolkit, from the design of programming languages and program synthesis and code that writes code. It's interestingly also somewhat related to older ideas of genetic algorithms and genetic programming, but it's different from that. It also draws on some Bayesian tools, but it's different from that. It draws on some techniques of programming language design and even techniques from compilers. So I see that area, for example.
So how could that match with evolution of intelligence in animals and humans, right?
Yeah, I mean, I think it matches very well, right? I mean, DNA is code, right? And a body and a brain is a machine that builds itself from some code. One of the things it does is it writes new programming languages, both individually and collectively. So I think that general idea is actually a very powerful one, and the many different versions of it can correspond to the different scales, levels of analysis, and scales of adaptive processes, including learning, biological evolution, cultural evolution. I mean, that's a very big picture, but I think that's one key difference, yeah.
Yeah, so I totally agree that programs are incredibly important, especially for human-level intelligence. But I wonder what you think about this idea that there are different levels of kind of intelligence, and abstract reasoning and programs is kind of the top side of that. But below that, you have more kind of grounded perception-based abstractions. And I think there was an interesting experiment by Luria where he kind of traveled around Russia at the beginning of the 20th century, asking people kind of abstract reasoning questions like, giraffes don't live in big cities. Moscow is a big city. Would there be a giraffe there? And people could not answer this abstract question. They were like, well, they were only basing answers on their personal experiences. Like, I've never seen the giraffes. I can't answer this question. So, and it seems like essentially this kind of reasoning was not present in people who didn't have formal education. And it seems like the formal education is what gives people the ability to kind of build programs.
That's one kind of programs. That's like the consciousness part. That's like symbolic propositional programs. But there's lots of other programs in the brain. In fact, I think we want to think about how to make perception really work, right? And in my view, and grounded, I'm all for grounded language as well. But I think a broad, a broad view of programs that embraces the strength of deep learning, together with the idea of generative models and symbolic abstraction. I think that's also the key to perception and grounded language. But that's my view. I think another interesting difference, though, is the relation of the engineering enterprise to the scientific enterprise. Part of that is like how much scientific detail matters. Does the whole connectome matter? Does spiking matter? And so on. But the other is what's the relation between the experimental world and the sort of theoretical engineering toolkit. And a nice thing about cognitive science is that, as opposed to the neuro approach, is that I can do those experiments in my lab or on Mechanical Turk. I can work actively with people studying infants or young children. And to me, that's important. It's important to say, okay, when I say I want to build a machine that starts like a baby and learns like a child, it's not simply my intuition about how children think, which is, Marvin Minsky, as brilliant as he was either citing his intuition or Piaget's intuition. But that, Piaget was more or less a contemporary of Turing, right? A lot has been discovered in the last couple of decades, and babies' brains, it turns out, they're not blank slates. They start with a lot of structure, and learning is a lot more sophisticated and a lot more diverse and a lot more symbolic, we think, than simply, gradient descent. And that's the science that guides what we do.
I have the impression that what you're proposing is to use the formalism which seem naturally adapted to System 2 computation in order to explain System 1 computation.
No, again, I don't want to miscommunicate here. Right? When I say programs, I don't simply mean Lisp programs, right? I mean a broad thing which includes deep networks, right? I mean, these days in my group, we do a lot of stuff with deep networks, and one of the things we do is we use deep networks to guide the construction of the symbolic layer, right? Mm-hmm. And I think that's very exciting. So I want to be controversial in the right ways, but I don't want to miscommunicate. I'm not saying oh, we should go back to symbolic AI. I'm saying they had a good idea. You guys had a good idea too. Judea Pearl had a good idea.
We need to put all these things together.
Laplace had a good idea around probability, right? And we have a maturing toolkit that allows us to see how these several good ideas
Absolutely.
fit together and actually can extend each other.
Maybe
extend.
I can propose a synthesis. I mean, I think that the symbolic is crucial, but coming towards the end rather than the beginning. So you have to build up to it. You have to sort of earn your symbols by first sorting out maybe unsymbolic representation. And good old-fashioned AI is a little bit like if you imagine some very low-tech primitive tribe that sees like a jet plane shooting across the sky, and they say, we want to build that. So they go directly, we want this high-tech civilization, and they put together like some wooden replica, right? It's never going to fly. The way to actually get there is to first invent simpler technologies, and then eventually you have factories and electricity, and you can do the whole thing. But it's still helpful, I think, when doing the sub-symbolic stuff to know what you're aiming towards, because it might be that you can have constraints in the kinds of grounded representations you create. If you know that in the end they have to be combinatorially.
That's what I'm proposing. That actually the needs of system 2 computation can be used to help system 1 representations to
define,
have the right structure.
Yeah, class functions for the representation.
Right.
I think it's
Actually, maybe let's take some
Yeah,
audience questions
that would be a
as
great
well.
idea, yes.
Yeah. I have lots of questions.
Max, do you want to, or, well, Vika, do you want to, feel free to, you guide the questions, go for it.
I loved how you guys on the panel put yourself on the spectrum of how brain-inspired you wanted your path to be, from very little to very much. And I would love it if you can also place yourself on a different axis in terms of how intelligible you're guessing that AGI is going to be. Where one end of this spectrum would be to say something like, well, it's just going to be ML all the way plus a bunch of clever new tweaks, but it's going to be a completely opaque black box. We'll have very little clue of how it actually works. To something maybe more closer to what Josh is saying, where maybe there is a lot of GoFi sort of married into that, maybe a lot of Josh's system too, so that we can understand more.
But there's going to be both, right? So if you look at humans and the system 1, system 2 distinction, there's going to be part of the explanation is going to be hard to express in words, and there's a part of it which is higher level, which gives probably a good approximation of the kind that humans communicate with language. But that's not going to be the complete explanation. Unlike what GoFi was trying to explain everything with symbols, to explain our actions or complicated decisions, there's going to be a part of it that remains difficult to communicate. That's what I believe.
Actually, to add to that,
If you're all on the same point on that spectrum, or if you have any disagreements about how pessimistic or optimistic you are about intelligibility.
so I think my view is that what perception does in biological intelligence is exactly grounding the kind of symbols, and then everything, even system 1, would then be built on top of that. So it's kind of disentangled representations that the perception builds first, and then you can do all sorts of things on top, either model-based planning or model-free RL. So even model-free might be more interpretable than just black box machine learning.
But some things remain out of reach of interpretability. Think about trying to explain the Go moves of AlphaGo, right? Maybe you can come up with, if it was trained with the constraint of having system 2 type of representations at a high level, you might come up with the same things you find in a Go book, but it's not enough to completely learn to do as well.
I don't think, I mean, again, I agree with what you're saying. On the other hand, explainability is a key part of human intelligence, right?
But it's incomplete, right?
Exactly, I agree with that. But we shouldn't underweight its importance. And
especially for AGI.
When a human player learns Go, they learn those explanations from the Go book or a master are crucial from the very beginning. And if we want a machine, if our goal in say Go or any other game is to build a machine not that ultimately with incredible amount of compute learns to do this one thing at superhuman level, but can learn more with the data complexity, as you said, and the time complexity of a human to learn so many different things so quickly, okay, then I think explainability is going to be a key part of that on both the input and output side. And I think, again, maybe we don't disagree on those things in terms of that's like the end point of the path. But in terms of where the paths are in the near term, this is where there is some difference. You're talking about earning your symbols. I think in certain ways that are not fully appreciated in the deep learning community, we already have earned our symbols. There's already quite remarkable things that we can do with symbols, and the deep learning people, many of them are doing it anyway. They just don't, like TensorFlow or PyTorch, symbolic languages that allow you to build, that allow an individual to build deep learning systems, and that allow collectively the cultural evolution process of what you call the deep learning community to innovate so quickly in what are very much like literally exponential growth counts, and you can measure them in people's Google Scholar counts and see it in the impact on the world. Okay, those are cultural evolution processes, which of course we don't know how to completely engineer those things in artificial systems nearly at those symbolic processes at the scale. But if you look at what's going on right now in other parts of the AI community, we have actually made real progress in machines that write code or machines that do probabilistic inference in code. So in the short term, I believe that it's not just the thing we're going to get to that we're going to have to earn and somehow is going to emerge out of networks. Right now, it is also on our route to building explainable AI and to understanding the explainable parts as well as the unexplainable parts, the more intuitive parts of human cognition.
I want to reply directly.
Maybe we should hear Eric.
Directly to Max's problem that about how optimistic we are for brain-inspired AGI. Let me give you a very simple example, but very intuitive. I think.
He was asking about how optimistic are you about explainable?
Interpretability.
We're all really optimistic.
No. I'm actually not for the long term, because the example is like this. I have a 2.5-year-old girl. There's one day when she said, "Dad, I'm gonna be a bad girl." I said, "What?" "I'm gonna punch you." I said, "No, don't punch Dad. I'll get hurt." So she thought a little bit. And then, so this is why I want to bring, I am bringing theory of mind and cognitive empathy to my robot so that it can get some autistic behavior. So I'm really worrying that once we have a model as a brain-inspired cognitive engine that have general intelligence as a human brain in a developmental way, but one day, even with autistic behavior, she said, I'm not gonna do this because I don't want to follow you. Because people do that. Starting from year one, they can have their free thinking, saying, I'm not trying that. So this is why I feel we still meet some dangerous point. Another example is human. Human is good from the broader sense, but talking about bias, who have bias? Human. So when simulating or building
so you
a
see there's costs, there's
cognitive
risks or costs, or there's
architecture.
limitations just being human cognitive brain inspired. Okay,
So we should study the neuroscience and cognitive science of bias and how to avoid that kind of a building block in
how to understand, yes. Well, some of them might be inevitable.
Yeah.
I mean, and some in any kind of inductive system, and others might be avoidable. And we have to study them to understand that.
Yeah.
Let's get more. Yeah.
So first off, great panel, and I like the discussion, the great part about the analogies and learning from humans and minds and so forth, and all the advantages of that. I want to just give some counter arguments and have you react to them a little bit. And let me just first off stipulate, I understand that there's existence proof and there's some benefits from the analogy, and as Irina said, it makes it easier to communicate. And Joshua mentioned briefly that maybe it's less risky because it's less likely to be bizarre. But from an economist perspective, there are some advantages to being very different. And first off, I mean, one of the reasons that bulldozers or jets are so valuable is that they have very different ways of generating power and so forth. And that's why they're much more valuable than a biological version of those machines. And secondly, maybe a little bit more subtly, if a machine is a close substitute for a human, then it makes human labor much less valuable. Whereas if it's very different, complementary, that has superhuman capabilities in other dimensions, but not on some of the things that humans can do, it's more likely to lead to an equitable distribution of income and wealth. It's more likely to have humans still be part of the valuable ecosystem. So it'd be interesting to have you sort of react to those benefits and costs of having systems that are very different from us versus systems that closely mimic us and gradually just are close substitutes.
So I can mention maybe the analogy of birds and planes. Yeah. It's the same underlying principles of aerodynamics, right? But of course, planes look very different. And you might argue that planes are better in some way, but actually they're just optimized along a different axis. So birds have lots of constraints of energy consumption that are not as present for planes. And we don't have planes that are as efficient at flying in terms of energy consumption. I think what's going to happen is we'll discover these principles, we'll make progress, and then these will be, of course, inspired by animal and human intelligence. But then we'll want to apply that intelligence to other things with different constraints than human bodies have. And then I think it will happen, as you say, that we'll move away towards, maybe even before we get AGI, right? It doesn't have to wait for AGI. In directions that are going to be different, that look different in nature, because we push in a sort of application where the constraints are different.
Let me make it even starker. I mean, if you suppose there's one path where AI researchers focus very closely on mimicking humans, that almost inevitably is going to devalue.
No, but I don't think that's what. I don't think that's what most of the, say, deep learning community is doing. We're not trying to mimic humans. So there's a big difference between mimicking humans, as in the details of what we do, of our failures, of our neurons, and getting inspiration and trying to get to keep that inspiration at an abstract level that corresponds to where we think are the right principles. And maybe Josh and I could differ on that. That's okay. We need to explore all the routes. So that's not mimicking, right? I think that the notion of mimicking doesn't work.
Can I just come in both with an opinion and moderation? So I agree with the points you're saying, both the value and the risk. Value of an alternative path and the risk of a certain path that's mimicking humans. I think another way to put the point is that I don't think any of us are interested in are working on building digital humans. But when we say there might be some key capacities of humans that we want to achieve human-level goals with human-like means. And for example, common sense abilities, right? Or certain kinds of social cognition that again allow us to talk, trust, and teach with each other. So if we could have whatever kind of AGI we have, if we want to be able to interface with it, if we want to be able to talk to it and trust, but that doesn't mean it has to be a full person. I think there is an interesting point. If you're actually going to build agents, your point about having a self is central. But we don't necessarily want to build AGIs that have a full human-like self. We might want them to have full human-like common sense, but not a full self. We might not want them to have some of the same, fundamental motivations and will that we have. And understanding, and from an engineering point of view, how that actually works in humans allows us to tease apart the components and engineer the ones we want, and not the ones that we don't want. At least that's one vision. So I think that's important to get clear. I mean, to go back to the popular airplane analogy, we should build airplanes, but some of the things we're building are also kind of more like robot birds, right? Like in some sense, agents that might lead the flock in the right direction. If there's birds that are flying, if there's robots that are flying around with the other birds, they shouldn't be like airplanes, because either the airplanes or the birds or both will die. We've seen that happen too, right? Or like in the self-driving car analogy, we could just right now, if we passed global laws that banned all human drivers and pedestrians and bicyclists from the streets and said everybody has to be in a self-driving car, it'd be a lot easier and safer in a certain sense to build autonomous vehicles. But because the route that we seem to be on is one in which autonomous vehicles have to live in a human world where there are humans driving and walking and bicycling and so on and leaving stuff on the road and whatever, then there's going to have to be, and I think most people that right now agree that this is a key bottleneck in autonomous vehicles, they're going to have some understanding of human intentions so that they can be safe and valuable in interacting in the world. And so that's the kind of thing that at least I'm talking about. That can be both economically valuable and safe.
We need to differentiate.
Yeah, let's.
Yeah.
Okay, good.
Yes, this has truly been a wonderful panel, and I've noticed that in quite a few of the conferences I've gone to lately that the need to bridge the symbolic and the neural-based machine learning approaches is getting emphasized as one of the next tasks, and also that there's this recognition that, at least in the learning of children, that it's much more embodied and much more robustly embodied, actually, than we may hitherto have understood. But in us humans, evolution forged us as creatures in which these capacities are deeply integrated. They're fundamental to us functioning as integrated beings, both integrated in ourselves and in our adaptive relationship to our environment. And so my question is, are we really just looking at these as individual capabilities and trying to forge them, or do we have pathways for robust integration within AI, or are in the end we get to get really kludges that do all of these tasks but don't integrate them very well in an embodied relationship to their environment?
Maybe I can start on that. So my view is that there needs to be integration, and we see that in humans, right? We see how our language shapes how we perceive the world, right? But at the same time, we can't, as I mentioned before, we can't necessarily learn language at the same time as we learn the kind of basic concepts. So it's like there seems to be this bootstrapping where we first need to have some basic understanding of the world from which we learn the symbols, which is language, and then language is what gives humans this ability to turbocharge our intelligence, because now we can move to the symbolic domain and manipulate, essentially create new structures just in the symbolic space, maybe using programs, and so that programs can only exist in the symbolic space, so that's where humans kind of start overtaking animal intelligence.
I would say yes, very much to the things you're looking for. That's the thesis that I'm talking about. We already have very interesting, promising first steps towards what you could call neural symbolic integration, right? Those already exist, and they're very important for embodiment. So, recently I found myself working with a number of robotics groups, and when I work with roboticists, what that usually means is, they do all the hard work of the engineering. But I'm very proud that a few robotics collaborators, we've published in the last few years a couple of robotics papers. 2 of them have won best paper prizes at leading robotics conferences. I don't claim any credit for that. But what they've done is they've actually, in different ways, some of them are using actually sort of, basically combinations of symbolic, and each of them use combinations of symbolic and differentiable approaches. One of them has no neural networks at all, but has differentiable dynamics, like differentiable physics dynamics, but then a symbolic planner that basically says which dynamic modes should you use. That was work that Mark Toussaint did. Another one, which was work that Anurag Ajay, an MIT student, did working with Leslie Kelbling and others, right, was one where he took an analytic symbolic physics dynamics model and then added on a neural network to learn the residuals. You can write down, we have really good physics engines that we can write down right now, which capture, are very powerful in capturing a range of different kinds of physical interactions, but they're not perfect. And there's many things that we don't know how to capture in their way, so the neural net learns the residuals, and that is a very powerful combination also. That already exists, and it's being used in real robots. So another example of paper that will soon come out in Science Robotics by Nima is an example that plays Jenga, that uses probability and symbols to play Jenga, right? So those are real things that are happening right now. It's incredibly exciting.